This is part 12 in our series of lectures on section 2.5 on other forms of induction. And in this lecture, we're going to demonstrate the logical equivalence of the principle of mathematical induction, the principle of complete induction, and the well-ordering property of the natural numbers. The result we're interested in proving is contained in this theorem. It says that each of these three principles of induction are logically equivalent to each other. So what that means is that if we assume any one of them, then we can use it to deduce that the other two are necessarily true. So in order to do that, we really only have to do three proofs. It's enough for us to prove that 1 implies 2, 2 implies 3, and 3 implies 1. So by that I mean, so 1 implies 2 means if we assume that the principle of mathematical induction is true, then we can deduce from that fact that the principle of complete induction is true, and similarly for the other two. I'll note that our textbook, as much as I like our textbook actually has two separate theorems. In one theorem they prove that these two are logically equivalent, and in another theorem they claim to prove that 1 and 3 are logically equivalent. So they actually prove four things. They work a little bit harder than they have to in order to do four things. They could have gotten away with just simply doing this if they did both of the theorems at the same time. The other thing is their proof that 1 implies 3 seems to me has a bit of a gap in it, and I think it's preferable to show directly that 2 implies 3 rather than 1 implies 3. I think it's a little bit easier. So let's begin by going over my proof that 1 implies 2. In other words, that the principle of mathematical induction implies the principle of complete induction. So assume the principle of mathematical induction holds. We have to show that the principle of complete induction holds. So suppose we have a set S satisfying these two assumptions of PCI, namely 1 is an element of S, and for all natural numbers M, if the set of all predecessors of M in the natural numbers is a subset of S, then M is an element of S. So PCI would be true if we could then deduce that S is necessarily equal to the set of all natural numbers. So that's what we have to prove. We have to show, just simply using PMI, that S is equal to the set of all natural numbers. So the way we're going to do that is we're going to introduce this set E. We let E be the set of all natural numbers N, such that N and all its predecessors lie in S. So let's now apply the principle of mathematical induction to E. So start with the basis step. Why does 1 lie in E? Well, 1 lies in E if you can show that the set of all numbers just consisting of 1 is a subset of S, and that follows from this assumption here. So 1 is an element of E, and that concludes the proof of the basis step. Now look at the inductive step. Give ourselves a natural number N, and assume that N lies in E. Then we have to deduce that N plus 1 lies in E in order to apply principle of mathematical induction. So to say that N lies in E is to say that this thing is a subset of S, right? Because that's the definition of E. That's the definition of what it means to say that N lies in E. But once you know this, then we're going to apply hypothesis B up here, where we let N be this M minus 1. So the assumption that this is a subset of S implies by this that N plus 1 necessarily lies in S, right? We're applying this assumption here where M minus 1 is N. Okay, so we've deduced that N plus 1 must lie in S, and that means that this entire set is a subset of S, because we already have assumed that the predecessors of N plus 1 lie in S. And that's exactly what it means to say that n plus 1 lies in E. So we've started with an element of E, and we've shown that the next highest element is in E. So it follows from principle of mathematical induction that E is all of n. And that means if you give yourself any natural number n, then this thing is a subset of S. And so in particular, n is an element of S. And so we've shown that any n in the natural numbers is an element of S, and that's what it means to say that S is equal to all of n. And so we've done what we had to do. We've deduced S is n, assuming just these two hypotheses and the ability to use the principle of mathematical induction. So that completes the proof of 1 implies 2. Now we're going to prove that 2 implies 3. In other words, that if we assume that the principle of complete induction holds, then the well-ordering property of the natural numbers also holds. So assume that the PCI holds, we must deduce from this that the well-ordering property of n holds. So give ourselves a non-empty subset of n, we'll call it T, and we have to deduce, using principle of complete induction, that T has a smallest element. That's what it would mean to prove that the well-ordering property of n holds. So we're going to argue by contradiction. Let's assume T does not have a smallest element. Let's let S be the complement of T. In other words, S is equal to the set theoretic difference, n minus T. So what we're going to do is we're going to obtain a contradiction by showing that S is all of n, and that would then imply that T was empty, contradicting that T is assumed to be non-empty. So we're going to take this set S, the complement of T, and we're going to apply PCI to it. So what must we do in order to deduce that S is equal to n? Well, we have a basis step. We have to show that 1 is an element of S. So why must 1 be an element of S? Well, 1 can't be an element of T, because if 1 were an element of T, then T would have the smallest, a smallest element, because 1 is the smallest element in all of the natural numbers. So since 1 can't be an element of T, 1 must be in its complement S. So that's the proof of the basis step. Now we look at the inductive step. Let n be a natural number bigger than or equal to 2, and assume that the set of all predecessors in the natural numbers are elements of S. We have to deduce that n is an element of S. So to say that all of these elements lie in S is to say that they're not elements of T. Well, if they're not elements of T, then it's impossible for n to be an element of T, because if n were in T, since all of its predecessors are not in T, that would mean that n was the smallest element of T, and remember, we've assumed that T does not have the smallest element. Okay, so n cannot be an element of T, and so by definition, n must be an element of the complement of T, in other words, S. So we've deduced that n must be an S, and therefore we've completed the inductive step that goes along with PCI. Okay, so it follows, finally, by PCI that S must equal all of n, and that's impossible because that would imply that T was empty, the complement of S would be empty, and we've assumed that T is a non-empty subset of n. So there's your contradiction. So T must have a smallest element. And finally, we're going to try to deduce that 3 implies 1. In other words, we're going to assume that the well-ordering property of n holds, and we're going to try to deduce that the principle of mathematical induction holds. So let's give ourselves a set S, having the usual properties for principle of mathematical induction. We have to deduce that S is equal to all of the natural numbers. So let's let T be the complement of S. T is n minus S. We're going to argue by contradiction. Suppose that S is not all of the natural numbers, then T would be non-empty. and therefore by the well-ordering property of n, T would have a smallest element. Let's call that smallest element n sub 0. Well, n sub 0 can't be 1, because by this assumption here, 1 lies in S, and therefore 1 cannot lie in T. So that means n sub 0 must be bigger than 1, so when you subtract 1 from it, you still get a natural number. Well, since n0 is the smallest element of T, n0 minus 1 must be a natural number that's not in T, and that means it's in S. So now we're going to apply this conditional statement where n is replaced by n0 minus 1. We've said that n0 minus 1 is in S, so according to this, n0 must also be in S. And that contradicts the fact that n0 is in T, right? Because S and T are disjoint from each other. They don't have any elements in common. One is the complement of the other. So that's a contradiction. And therefore, this cannot be true. Therefore, S must be all of n. And therefore, we've deduced that the principle of mathematical induction does indeed hold. That completes the proof.